Okay, so most of the text in this question is actually statements. It's just sort of laying up context, and it's saying, so in the single variable context, we observe that the curvature is equal to the magnitude of dTds. So we're going to use that as a motivation to define curvature in R3. Right, so we're basically defining or setting up, here it is, this picture that we've got this dTds vector, and we're going to define its magnitude to be the curvature, and I guess it also observes that means that it's curvature times that vector that we're calling the principal unit normal vector. Okay, so that's just sort of justifying the picture, really. Okay, so now here's where the actual question starts. Use the fact that t dot t is a constant, so that's going to be our starting point. And then our goal is to show that dTds is orthogonal to t. So, okay, all right, so here we go. So t dot t is a constant. Okay, first of all, is that true? Well, t dot t is magnitude of t squared, and t is defined to be a unit vector, so the magnitude is 1, so that's 1. Okay, so this is our starting point. We're going to start with the fact that t dot t is equal to 1. Now, the next thing that that we observe here is that I want to show that dTds is orthogonal to t. So I would like to see dTds dot t. So if I could compute this, then I'd be in good shape, right? Because showing that two vectors are orthogonal, a good way to do that is to show the dot product is 0. So I look at what I'm given. So I'm given information about t dot t. I want information about dTds dot t. See what I'm saying? Right. So the motivation, you see the connection between what you're given and what you want is take the derivative with respect to s. So what I'm going to be doing is I'm going to take this expression that I'm given. Whoops. I'm going to take its derivative with respect to s. So let's take the derivative of both sides of this equation with respect to s. Okay. Well, we have a dot product, and we're going to use the dot product rule. And that gives me dTds dot t plus t dot dTds. That's just using the product rule, the dot product rule on the left side of the equation. And that equals to the derivative of 1, which of course is 0. Everybody good? By the way, there's a chair here if you want to. Okay, suit yourself. Okay. Okay. Well, now, good news. The product rule is, commutative, right? You can. Sorry, the dot product is commutative, so you can switch these around either way you like. So really, what we have is 2 dTds dot t is equal to 0, and you cancel the 2, and you have, as desired, that dTds dot t is equal to 0. And that means that those two vectors are orthogonal. Yep.
Sorry, I missed the part. So how did you get dt dot, or ds dot t plus t?
How did I get this? Yeah, so that's using the product rule. So we're taking this purple equation here. Let me get this out of the way. We don't need that anymore. I'm taking this equation and taking the derivative of both sides with respect to s, and you notice we have a product on the left side, and there is a product rule for dot products. And in fact, come to think of it, it might be, yeah, here it is. So it was from an earlier question. Does it make sense? Yeah. Mm-hmm.
Can you explain where you got the 2 from?
Yeah. So, this and this are the same thing. Yeah.
Yeah, okay.
And so therefore, yeah. Okay. Is everybody good? Yeah, go ahead.
Yeah, so we actually didn't need to use like the
Yeah.
KN.
Yeah. Most of that text there was just kind of lead in to why we'd be interested in such a thing. Right. Yep. Okay. Everybody's happy. Okay. Stop the recording.